There you go.
Okay, there we go. So it's a pleasure to have here today Professor Nancy Sandler from Ohio University. So Professor Sandler got her bachelor's in Argentina in 1993, her PhD at Urbana, Illinois in 1998. From 1998 to 2000, she had a postdoc in France, in Paris. And 2002, she had a postdoc in Boston, in the US. And from 2005 to today, she's at Ohio University, and she's a full professor there now. The title of her talk is Bumpy Graphene Membranes, a roadmap for flatband engineering and percolation of topological states. So Professor Sandler, it's a real pleasure to have you here with us, and the microphone is yours.
Okay, thank you, George, and thank you, Edson, and thank you, everybody. It's really nice to be in touch again, even if it's virtual. I hope that the next time I will be there enjoying the weather, the people, the food, and in that order. So I really appreciate, especially, I appreciate the fact that you waited for having me to give this talk, and this is the disclaimer. I am going to present results on our latest work. It's a topic of a manuscript that is in preparation now, that had puzzled and confused us for a long time. And because of that, I would like to ask for feedback, because this is the first time that I'm going to tell this story, and it's full of subtleties. So I would appreciate if you could interrupt me with questions along the talk, make comments, so I can clarify and the message is reaches and it's well delivered. So let me start with a fast and brief introduction to why we are looking at deformations in graphene. Graphene is very easy to deform, being a monoatomic membrane, and it has been, the effect of deformation have been observed since the very, very beginning, long time ago, with these experiments of graphene on complexes of platinum atoms that were on top of a surface, and STM images were able to picture these little mountains or hills in other substrates that show in the bottom like little pyramids that cannot be perfectly resolved in the main panel, but can be resolved here. You see like the triangular shape that were breakings on the substrate, and graphene deposited on them have been accommodating to the surface. Thermal treatment produced rugosities, scraping of graphene make the membrane to get out of plane and bend or fold in the third direction and create kind of nanoribbons that self-build. When graphene is suspended, it's very easy to deform by stretching and compressing it. And of course, the standard is to deposit graphene on substrate that have been engineered or prepared so that graphene accommodates when it lies on top of a surface, like in these experiments many years ago. As you see the dates of these experiments, this idea of trying to understand how graphene behaves under deposition or under thermal treatment or suspended, and how it behaves mechanically and the electronic properties have been the topics of research from long ago, and we have a very deep understanding, I would say, of many of the properties that the material presents. In particular, we have been focusing in my group and with my collaborators, we have been looking at the electronic properties, and basically we have been trying to understand the electronic properties from a very basic point of view, with a theory model that captures very, very few essential elements, and that in principle appear to be enough to describe these electronic properties. And let me, for those of you who are not familiar with this, I will briefly review what the idea is. Here I am showing a graphene membrane that is under the deformation, gets out of the plane, so it goes in the third dimension. And the idea is that this modification in the positions of the atoms can be captured by how these nearest neighbor vectors or nearest neighbor bonds get modified as graphene stretches or deforms and it gets out of plane. These deformations can be cast in terms of the positions, the new positions of the ions. And the idea is that these displacements are small because of all the chemical constraints imposed by the bonds. And because the displacements are small, the whole thing can be the new positions are the new lattice vectors that indicate the new atomic positions can be described in terms of the elasticity theory, where we use the strain tensor. Now, for a standard model of electrons jumping on this lattice that we use the pi-binding Hamiltonian, this modification entails to modifying the Hopin matrix elements by an exponential factor that depends on the elastic properties of the membrane, given by this parameter beta that for graphene takes the value of 3, and the new lattice distances, basically, between the atomic positions. Now, this behavior, this change in the Hopin parameters resembles a lot the way that we treat electrons in a lattice that move under the influence of an external magnetic field. And this is one of the reasons why people try to cast the effect of strains in terms of effective or pseudo-magnetic fields. This description is clearer when we go to the continuum model. In the continuum model, we basically take the band structure of graphene, the energy momentum relation, and we linearize it. We look at it, or we exploit the fact that it's linear around these 2 points that are known as K and K prime, or Valley points, and have a spectra that is linear. So we have fermions with linear dispersion, and these fermions that should describe the effect of the atoms in these 2 units or 2 atom or 2 atomic unit cell in the real material. These fermions will have 2 components to indicate what happens with the electrons coming from each atom, the ones that occupy the 2 inequivalent lattice points. That's why we say we have fermions with a spinor structure, and that's why we describe the dynamics of these fermions with the Dirac equation that is represented by the first part of this equation here. Now, because we have 2 different K points, we will have 2 effective continuum Dirac Hamiltonians, one corresponding to each point. Okay, so it's like we are splitting the electronic wave functions into 2 parts, if you want, and the dynamics of each part is described by these terms in these 2 Hamiltonians. And the strain that is incorporated in terms of the changes of these nearest neighbor Hopin terms, that gives rise to 2 different combinations in terms of the strain tensor that are usually considered as components of a vector object that is known as a pseudo-vector potential. Now, this pseudo-vector potential is basically representing the strain, and this strain can be homogeneous, that is independent of a spatial position, or can be inhomogeneous. If it is inhomogeneous and it has a variation in space that gives rise to a curve, then we talk about the pseudo-magnetic field. And in this picture, basically what we are saying is that the effect of a strain can be represented by a pseudo-magnetic field that changes in space as the strain changes in space. Now, if you look at the strain tensor mathematically, these are not the only components that appear or the independent combinations that you can make. You can also have the trace of the strain tensor, and this one also has a physical interpretation in terms of a scalar potential for the electrons. And the simple intuitive way to see this scalar potential is to consider a unit cell in graphene and thinking that if you stretch the material, you increase the separation between the ions and you are eliminating electronic charge from the unit cell. So to keep charge neutrality is equivalent to have a gate potential there. And this is what this term is mimicking. And these are constants that depends on the material. So basically, electrons moving in the graphene lattice in the presence of a strained field, a generic inhomogeneous strained field, can be represented or can be described in terms of effective Dirac fermions with a spinor structure. The spinor structure represents what happens at each sublattice in the unit cell, plus a scalar field. Now, if there is a magnetic field spinor structure and a magnetic field. If there is a pseudo-magnetic field present, let me just, for comparison, show you what is the expression of the Dirac Hamiltonian in the presence of a real external magnetic field. And the main difference that I want to point out is that with the real magnetic field, the sign in front of the pseudo vector potential doesn't change as it happens here. And this change of sign is an indication of the fact that this is not a real magnetic field. It's not acting on the orbital degree of freedom as a real, or on the spin degree of freedom in terms of a symmetry. This is an artifact of the mathematical description, but it's a very useful artifact. So the question is, in this picture, can I understand the signatures of a strain in terms of the same signatures that I have with a real magnetic field? Well, in a real magnetic field, we know that the levels, the energy levels, this is the total density of state of graphene. When you have a real magnetic field, it gets redistributed. The states have changed, are redistributed, that they pile up in a set of bands, separated bands, isolated bands that are called Landau levels. And the spacing between these levels, these bands, follow a very well understood scaling that goes with the square root of the field. The existence of these bands and the scaling has been observed in many experiments. I'm just plotting here two experimental data from STM measurements where they check the scaling with the magnetic field, and they check what happens or how these bands appears as you increase the magnetic field and how they separate. Now, something that I want to stress in this picture is the fact that in contrast to the Landau level spectra observed for two-dimensional electron gases, the Landau level spectra for graphene has a zero level. That is, there are states at zero energy, which are the states that exist at these valleys, KK prime points here, that are degenerate states. In these points, we have bands crossing. We have 2 degenerate states per spin here, plus 2 degenerate states per spin here. And these states come up to fill half of this zero energy Landau band. Now, the fact that there is a zero Landau band is another manifestation that graphene doesn't have a gap in the spectrum and will have conducting states at zero energy, where zero energy is the energy where the chemical potential is for the pristine material. Okay, so this zero energy Landau level will play a crucial role in the story that I'm going to tell you. Now, these features that exist in a real magnetic field have also been observed in STM measurements for graphene distorted or on top of substrate that has rugosities. The scaling has been confirmed, the emergence of Landau level peaks have been conserved, and this is why we think that the picture of a strain graphene in terms of a pseudomagnetic field is solid. Okay, it provides a very good representation of what happens with the material. So we studied this for a long time in terms of isolated deformations, and we focus on deformations that were local and had a Gaussian shape. And what we showed was that the charge distribution where you have this type of deformation is very peculiar because it produces, for this particular model, it produces a distribution in the density of state that follows a pattern like this that we call flowers. So the charge gets enhanced per sublattice in different regions on space, where here we have more charge residing in one type of atoms, and here we have more charge residing in the other type of atom in the unit cell. And this charge separation in real space has consequences in the separation of states coming from one valley and from the other, and this gives rise to the whole field of valleytronics that is a completely whole area of research for many people. So, knowing that we have this change in the band structure when we have constant homogeneous fields, and knowing that the charge have this weird distribution, well, it's natural to start thinking is, can we design the band structures? Can we introduce changes in the band structures as we want if we strain graphene appropriately? And the answer to that question, sure, you can do that. You need to have a strain all over the place if you want to modify the band structure, because remember that the band structure is the property of the periodic system. So we cannot have a local effect like the ones that we spend a whole time studying. So basically what I am saying is that if we want to modify the band structure of graphene, what we need to do is to do engineer substrates. And this is not a crazy idea. This idea has been in the air for a long time. This is an example of an engineered substrate in which graphene is deposited on top of a substrate that is made out of boron nitride with gold pillars sitting in an hexagonal lattice. And this is a picture of how graphene looks on top of each of these pillars. These pillars have a diameter of 100 nanometers roughly. So graphene on top of the pillar is rather flat, and the strain is more pronounced when graphene falls from the pillar. And if you look at the micrograph of a larger structure, you see that the flat areas are identified by these circles here. And between the circles, we have these folds forming, okay? It's pretty much similar to when you have a bed sheet and you hang it outside to dry in the sun. No, the folds that form resemble pretty much what happens on graphene. Another experiment where they design kind of a substrate and they follow what happens with the graphene membrane, where they drew nano prisms in silicon carbide, and they were able to show that graphene falls into the prisms, into these prism-like holes. And of course, there is a huge strain in these areas where the membrane has to accommodate to the underlying substrate. There is another experiment, a more recent one, where they deposited graphene on a bed of silicon dioxide nanospheres, which are insulating. And these nanospheres have a diameter of roughly 20 nanometers. And graphene, as you see in this picture, it accommodates on top of the nanosphere, creating a rugosity that follows the closed packing of the nanospheres in the bottom. These previous experiments, the ones on top, they did STM measurements. So they were trying to characterize electronic properties by STM measurements. In this experiment in the group by Nadia Mason in Illinois, they did transport. You see that they have contacts here, and they did transport, and they, when graphene is on top of a normal substrate without rugosities, they obtain magnetotransport. This is transport as a function of the magnetic field and the density of states, how the conductance go, and they see the Landau levels. But when graphene is strained by these rugosities, they find a reconstruction of Landau levels here, which in principle could be understood by the strain caused by this structure. Now, this work basically was the original motivation for our work. Contacted us trying to understand the fine details on these pictures. And we thought, yeah, this should be an easy problem to attack. So for the students in the audience, if your advisor comes and tells you, hey, this is an easy problem, you will be able to solve it in a couple of months and we can get back to these people, be very distrustful. Don't trust what your advisor is telling you, okay? So be aware that when your advisor comes and tells you this is easy, 99% of the time it's not easy. It's not simple. So be very, very skeptic, no, of the proposal. A more recent experiment along these lines was done, it's going to be 2 years ago, where they also found a periodic structure of graphene deposited on another material. In this time, the material was niobium diselenide. And because of the thermal treatment and the fact that these two materials have different thermal properties, the graphene on top of niobium diselenide buckles and forms this structure that looks pretty periodic in this micrograph that has an extension at most of 50 nanometers. So it's not a large sample, let's say, and if you analyze it carefully, it's not truly periodic, meaning that the distances between these two points are not exactly the same. But at this scale looks periodic. You have 3 traces that show certain periodicity, and you can start thinking that, okay, graphene here is a strain. It buckles out of the surface in a situation that looks reminiscent to this one, except that the size of these circles are much smaller than these ones. So in principle, this should be more strain. And these experiments were reported the existence or the emergence of type of flat bands due to the strain produced by this structure. However, they were not successful in correlating the geometrical structure of the surface of the material with the type of strain that was needed to input in the model to match with experimental data. So at the end of the day, they matched experimental data proposing a particular pseudomagnetic field profile that didn't correlate with the geometric structure of the membrane. So it wasn't clear, at least for us, what was the real explanation for the interpretation in this data. So we said, okay, let's start looking at this. Instead of looking directly to a fully periodic structure, we said, since we have experience with Gaussian-shaped things, let's start putting Gaussians together and let's see what happens. Let's use the continuum model so we can do analytic calculations, and let's put two Gaussian deformations and let's separate them, change the parameters. We did all the games. We played all the games. And as you can expect, when you have two deformations, the theory is linear in the fields, which means that the total pseudo-vector field that you're going to have within this description will be the sum of the independent ones plus the one resulting from the overlap, and the same with the scalar fields. And you can apply the same machinery and do the same type of calculation for Green's functions. You think about this in terms of a scattering problem, calculate Green's function, calculate the density of states from the imaginary part, and you start getting pictures, right? So in this slide, I am showing the pictures for the shape of the scalar potential and the pseudomagnetic field for one isolated deformation and for two isolated deformations. And you, as expect, you lose the rotational symmetry that you have before because you are selecting one direction in space by the direction in which you put these two things together. But in addition of that, you are increasing the effect of the changes or the magnitude of the fields in the overlap region. Okay, so you expect now that when you start putting things together, then the action doesn't happen in the isolated lobes, but it will start happening in the overlap regions, and they will play the main role here. So again, some idea of how the local density of state changes when we go from one deformation to two. The dotted line here represents one deformation. The solid line is two deformations. This is a change due to the scalar field. This is a change producing the density of state because of the pseudo vector field. And you see that they are two different trends here. But what I want to stress out is the magnitude in the change of the local density of state. This is plotted in a unitless measure, so we can compare. And you see that the change produced by the pseudo vector field, these components, combinations of the strain components that make this quantity, is 2 orders of magnitude larger than the scalar one. So when you add the effect of both, basically the change in the local density of state is dominated by the pseudo vector field, and that's why we tend to focus on this quantity more than the scalar one. So these are pictures of how the local density of state looks like if you do STM. This would be if you only had the effect of the scalar field. This would be with the pseudo vector field, so the total will be a superposition, but as I said, this will be the dominant one simply because of the magnitude of the effect. And you see that when you have you plot the local density of state at a certain energy, and at this energy you see this pattern, so the flowers start repeating. At a higher energy you start seeing the formation of different type of structures that look more like one-dimensional. So depending on different energies, you start redistributing the charge in different spatial patterns, which makes sense because you can think of the states having different momenta, and the momenta compared to the size of this deformation region will be affected differently. So fine, looks fine. Let's start adding more deformation. Let's see how far we can go with Gaussians. We have 3 here. We have 4 at a given energy where we have the flower pattern repeating. At a different energy, we have this one-dimensional pattern. But again, you see that when there are energies, and I am putting these energies on purpose, obviously, where the change in the density of state is much bigger than at other energies. So there is a bunch of states that are most effective, if you want, and these bunch of states are the ones that tend to reproduce basically a similar pattern of the underlying magnetic field. we said, well, we put them together in a line. Let's put them together in a two-dimensional pattern. Let's do closed pack structure. So we have 3 bumps here, 4 bumps, how the black dots here are representing the center of the deformations. And you see, as we suspected from the beginning, that the main action happens in the intermediate regions where the overlap happens, okay? The maximum number that we dealt with this approach were 7 bumps, 7 deformations. Here, unfortunately, when we did this picture, these points indicate the positions for other plots that I am not including. By the center of the deformations corresponds to here, 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 and there. And again, the maximum effect occurs in the overlap. This has to be compared with the structure of the pseudomagnetic field that we have for this type of closed pack 7 bump structure. And something that I want to remark for this pseudomagnetic field is the fact that inside the pseudomagnetic field alternates in sign in a very short range wavelength, if you want, goes from negative to positive, negative to positive, negative to positive, while on the edge, it develops extended regions where it looks a little bit more constant. And if I think about constant in space, okay, homogeneous magnetic fields, what I think is, it's very likely that Landau levels will emerge here. While here, I wouldn't talk about Landau levels because the magnetic field changes very fast, okay, or in a very short length scale. So I don't think that the Landau levels can necessarily emerge here. This is a plot of the local density of state at the different energy, where the states are more localized here. And I would expect, well, if I were to put an STM tip in this area, I probably will, there is a chance that I will see Landau level scaling in my peaks in the STM. If I look at the density of states versus the energy, I will find a feature that looks like this. The pristine graphene will have a linear density of state. With 7 bumps, the density of state will have a bump at a particular energy, which happens to be this, which tells me that there is an accumulation of states or accumulation of charge if these states are occupied at particular energies. And that brings to mind, maybe I can localize these guys. Maybe I can create kind of individual local quantum dot regions inside graphene. But with a finite system size like this, there is not much more that we can say. So we say, well, there is no more solution that to go to a truly periodic structure, okay? And a truly periodic structure means working with something that is extended all over the space. Or, if you want, that imposes a superlattice structure. It acts as a superlattice potential on the graphene membrane. So we said, well, we are going to represent this modulation in the graphene membrane by a function. You think periodic, you see cosine. So we said, let's do cosines in general. The amplitude of the deformation will be given by this H0. And in particular, I am going to talk about one superlattice structure that will have hexagonal form, okay, will mimic the graphene structure. We have studied other superlattices, rectangular, square, oblique. But in this case, I'm going to think about the superlattice that is hexagonal. This is the representation of the superlattice in the real space. This is a highly exaggerated picture because the period of the superlattice that we are looking at is 14, 20 nanometers. So there are many more carbon atoms inside than the ones that are drawn here, but this is like a schematic picture. And this is the corresponding mini Brillouin zone, because once you have a periodic potential imposed on your graphene, you will have a Brillouin zone that will be much smaller than the original graphene one, where with its own symmetry points, these are the gamma S, Ks, and K prime S. I am going to differentiate the K and K prime points of the superlattice from graphene by this subindex S here. In this expression, so I mentioned this will represent the maximum amplitude of the deformation. These are the lattice vectors describing the structure of the lattice that I am looking at, in this case, 3 of them. This alpha I is a prefactor that will help us to study potential anisotropies in this lattice. Let's say that the lattice is not perfectly isotropic in all directions. It's anisotropic, and with this factor, I can modulate that. For the rest of the talk, this factor will be 1, okay? We will consider isotropic lattices, but later on we studied its effect. And finally, we have this angle theta. So when I have two lattices and I put one on top of the other, I need to describe how they are aligned, the relative orientation of one with respect to the other. And in the way that we chose the alignment is such that the value of theta corresponding to 0 degrees is when the two zigzag edges of the lattices are aligned. So when this A1 vector of the superlattice goes along the zigzag direction of graphene. When the graphene is rotated with respect to the substrate, this angle will change. So for those of you who are familiar with the physics of bilayer graphene and twisted bilayer graphene, what I am doing here is something very, very similar to what the games that people have been playing for twisted bilayer. I am going to change the orientation of graphene, not with respect to another graphene lattice, okay, but I am going to change the orientation of graphene with respect to the substrate, okay, that has a lattice shape, and I am going to study what is the effect of this misalignment or change in orientation. So just to show two particular configurations of the membrane when it's fully aligned with the substrate, that is theta 0 degrees, when it is misaligned by 15 degrees. Okay, so if you want when we go through the end point or the middle point of the bonds in real space, and basically you don't see much. Okay, they are not fantastically different. You have hills and valleys. The color scale is the same. So here the hills are green, the valleys are bright pink. Here the valleys are not as bright, so they are not as deep, if you want. But yeah, basically a bunch of hills. The thing that I want to remark is that at this orientation, if I chose the 0, 0 or the origin, the 0, 0, the coordinate 0, 0 here, the origin, indicates a maximum, the top of a mountain, which is this point here. However, if I am misaligned, the 0, 0 doesn't correspond to a maxima point, okay? So it's kind of the dephasing between these two directions is what produces different patterns. Now, what are the associated pseudomagnetic field profiles that these different orientations produce? Well, I here plot the pseudomagnetic field profiles for different orientations. They are perfectly aligned. I move them 7.5 degrees, 15 degrees, 22, 30, and 45 degrees. This is data for a modulation that has this height and a period of the superlattice that is 14 nanometers. Okay, so this represents a typical strain of 15% or so, a high strain, and we are plotting these values just to make the effects more noticeable. Now, if you see the aligned version, okay, when the two lattices are aligned, you see that the pseudomagnetic field profile has kind of a similar shape as to the Gaussian. It alternates in sign between positive and negative, and it allows us to distinguish a superlattice with two sides, two inequivalent sides that I am going to refer to as A and B, in analogy to graphene. These are not graphene atoms, because this region involves a lot of graphene atoms, okay? But the separation in the strain profile creates these regions which can be described with a magnetic field that is positive with a maximum magnitude of 620 Tesla, and regions where the magnetic field is negative, the pseudomagnetic field is negative and has a magnitude of minus 620 Tesla. Something that I also want to remark is that these white lines represent the equipotentials of the field, that is the places in real space where this pseudomagnetic field is 0, meaning that the strain is 0, basically, okay? These are singular lines, and they cross, and they expand for all over the surface. As I start rotating graphene, I start noticing that these profiles change, get modified. the first thing that I notice is that the equipotentials become closed lines, okay? Here, the white ones. And now I can define a distance between the vertices of the equipotentials that I will label with the letter L. The other thing that I noticed is that the maxima and the minima of the magnetic field are not the same anymore. So the magnetic field is not symmetric. What does it mean? Well, it means that if this is a high magnetic field, and I can think of kind of a valley, the height of this valley is not the same as the depth of this hill, the height of this hill is not the same as the depth of this valley. Here, the two were equivalent, okay? I went as high as I went down. But in this case, I start to get in an asymmetry. Here I have higher barriers than deeper valleys. When I go to 15 degrees, the thing gets worse. The anisotropy between up and down, okay, gets larger. The barrier, the magnetic field hill becomes very, very high, and the valley is shallower. The equipotentials here form lines that have larger symmetry than these ones. Okay, this figure has a larger symmetry than this one. And what I notice is that these regions become to start to develop the structure of a triangular lattice, while the hill regions develop a structure of a Kagome lattice. I keep rotating, and I go to the opposite of this. I lose symmetry here. I keep rotating. I recover this situation where the magnetic field is fully symmetric, but with a pattern in which sites A and B have exchanged places. And I keep rotating, and I get to something equivalent to that with the same asymmetry, but now the valleys have become very deep, and the barriers have become very shallow, or shallow, not very. Let's take the very out. And you see that they have kind of exchanged places. Here, the valleys are the ones that have the connectivity of a Kagome lattice, while the hills are completely isolated and separated. Okay, so this is a structure of the magnetic field. Any question?
Yes.
Yeah.
I think it's more natural if I understand this panel A. It's more natural because somehow some spot compensate the other magnetic, so the magnetic field. So maybe it's a little bit of stretch. This will preserve time reverse some sort. So, but now if you don't if you don't compensate anymore, the dip is not as deep at the height. So it's somehow having net magnetic field.
That's right. And this is at one valley, at one graphene valley. Okay, so remember that in the continuum model, we separate the physics into valleys, and each valley has different sign for the pseudo vector field, which represents opposite signs for the pseudo magnetic field. So this picture that is at valley K, let's say, changes sign when I go to valley K prime. So in one valley, I have an effective magnetic field that is exactly compensated by the magnetic field that appears in the other valley, and overall, we don't break time reversal. But I have a local time reversal. Yes, you're right. And this is, thank you for that, because I will get back to that, okay? Okay, so you say, well, I have the Hamiltonian, I have this, from this I can calculate the strain, from the strain I can calculate the pseudo vector potential will be a periodic function, I can use Bloch theorem, I put this into a computer, I can diagonalize a matrix, I can get the band structure. Since I have two Hamiltonians, I will have two band structures. One, the one that I solve at K point, and the other that I solve at K prime point, okay? And this is a band structure that is plotted following this path in the mini Brillouin zone. So I'm going to gamma, and I see that I forgot here the S indices, but this is gamma to K, S to K prime S, and back to gamma. So this is the path that I am moving. And again, if I think of the original band structure of graphene, when I have the superlattice, what I am doing is folding. And when I fold, I will create extra Dirac points when the bands cross. So the K point of graphene corresponds to the gamma point of the superlattice. The K prime point of graphene corresponds to the gamma point of the superlattice. And these additional Dirac points that pop up here are due to the folding of the superlattice, okay? And because of time reversal, if I have a Dirac point in this point, I will have a Dirac point there. The two band structures have to be a mirror reflection of each other because I didn't break any symmetry. I just impose a periodic potential. Now I start rotating, and I start rotating, and I see that these new Dirac points start opening gaps. And they open up exactly in the same way. I still can distinguish the bands from the K point from the bands from the K prime point, okay? I start rotating and the gaps get larger. And when I get to 15 degrees, the gap is the same at both K and K prime point in the superlattice, and this band becomes flat. It's as flat as you can consider this width to be small, okay? But what you see is that you now have a bunch of flat bands that are separated by gaps. So the first question is, are these real gaps, or the crossings that I had at the beginning move away from the path that I am going, okay? They are away from my Dirac, from the mini Brillouin zone path that I am plotting. Maybe they cross somewhere else, okay? So in order to verify that we have true to God gaps, you need to calculate the total density of states, okay? And this is a slide that I put to show all the figures together, okay, where blue and red represents the two valleys, K and K prime, and you see that for 15 degrees, something that again happens at 45, the bands become completely degenerate. Both valleys contribute exactly the same thing to the bands, okay? So this is the message of this slide. We calculated the density of state, and effectively for 0 and 30 degrees, we have these mini new Dirac points, and the density of state doesn't show any gap. However, for 15 and 45, there are solid and robust gaps separating the bands. So, good. We have a direct connection between the geometrical shape of the membrane and the band structure engineering. Give me a geometrical shape, I can give you the band structure that you are going to get. If you want gaps here, I will modulate my structure. So, perfect. The next question that we ask, what happens with the charge distribution? Where are these states located? Okay, so, okay, let's calculate the local density of states. And of course, we calculate the local density of states at energies that corresponds to the places where the gap opens, because we wanted to see in real life how this charge changes position in space as the gap is open, okay? So these are plots for the density of states on sublattice A. This is a superlattice site A, B, and this is the total. The contribution from both valleys, both graphene valleys, is the same for the local density of state. So for the valley, K corresponds to this point where the gap is. For the K prime corresponds to this point. So we calculate the contribution for both, and this is what you get. Something to take out from this picture is, again, I am plotting the equipotentials of the magnetic field as lines. So these circles are equipotentials. And you see that basically the charge accumulates in regions surrounded by equipotentials. There is a depletion of the density of state in the middle, okay? There are regions where there is no electrons, and the electrons tend to accumulate in this triangular shape, kind of, okay, in equal quantities, okay? So if I rotate this by 180 degrees, I wouldn't see any different, the same, or 60 degrees, I will see the same distribution. So I start rotating. I see the effect of the equipotentials becoming closed lines. Sublattice A change this way, sublattice B changes this way. This is the total thing. This is when the gap opens, and I am now plotting at the energy of the lowest band, okay? The top energy in the lowest band, which I will call the first conduction band, okay? That's where this density of state looks like. I keep rotating. This structure becomes more circular. It gets separated. You see, the density of states gets very, very low in the intermediate regions with depletion in particular regions. And I have these weird structures. And when I get to 15 degrees, I have a density of state that is distributed in two different spatial patterns, very, very different. One spatial pattern is described by a triangular lattice, which are these circles here, okay, where the density of state is high. And another pattern is this surrounding area that has the connectivity of a Kagome lattice, and it's physically separated from the other because here I have full charge depletion. So I don't have electrons here. That's what I mean, in the black areas, okay? So these two structures are disconnected. I achieved a full charge separation in real space in two different moiré-like structures. Well, that was puzzling, okay? This is a summary for going beyond 15 degrees, just to check that things are periodic. You see that you recover for 30 degrees, you recover what happens at full alignment. So you go from zigzag, rotate 30 degrees, you go to the other zigzag, the armchair, and you get the exchange of one sublattice by the other. They change roles. You go from zigzag to armchair. In 15 and 45, you get circles here for one sublattice, connectivity for the other, and at 45, you have connectivity for one sublattice and circles for the other. So they exchange roles. So the question is, what are these states that are separated? Are they Landau levels?
There's one
You
more
say,
question.
well, yes.
I interrupt you once again.
Yeah,
so
no, it's okay.
I discount my question at the end of the talk. So, but this is for a particular, you set a particular energy. What's the meaning that, why do you have it in special in this energy, 15, around 15 electron volt? 16 actually. Ah, all right.
Go back to this.
Nancy.
Wow.
Yes.
Nancy, apparently your camera is interfering with the audio. When you approached the camera, it started clicking and your audio was being cut.
No, I don't think it's that.
No. Okay, let me answer. Are you hearing well?
Yes, I hear well.
Yes, yes. So let me answer a question, see if I can close things.
This happened before with the camera. Was a problem with the camera, but I don't know if that is the case.
So I am interfering with the tablet and the computer, but let me know if it happens. I'm touching.
It's happening. It's happening now.
Yeah.
It's a clicking sound. It's a clicking sound that covers your voice.
Yeah. It's not responding.
Yeah, I think just because I asked it.
Okay. See me? The other. You, George.
I can't hear you because
Okay.
I don't know what is causing that. Now it's 0.
You are muted for something.
You're muted. You're muted.
No, cannot hear.
Nancy, I can't hear anything. Zero, zero, zero.
Okay. Can you hear anything? I don't think she can hear us. Nothing. Yet?
Can you hear me?
Yes.
Yeah. Now we can. Now we can.
Okay, great. So I was trying to answer the question. For 15 degrees, what you have is this particular flat band that is not fully flat because it has dispersion here. Let me see if I can use the laser pointer. You have dispersion here, you see? It's not fully flat, but in this region is flat. And you have some type of symmetry between what happens at K prime and K in the mini-Brillouin zone. This doesn't happen for here, for instance. When you see that what happens at K is different from what happens at K prime. So as you rotate, you start with no effective time reversal symmetry, if you want, between these two states, and you develop this effective time reversal symmetry for particularly 15 degrees and 45 degrees. This is what happens. But I think that this will become clearer later. So let me go on a little bit more. So the message that I want to convey is that this charge distribution that is very peculiar, if you want, and is periodic, the question that we ask, these should be Landau level kind of things, okay? So if they are Landau levels, the separation between these flat bands should follow some type of Landau level scaling, right? So is any information about these particular states in the band structure besides the gap and the fact that they are flat? So when you ask about these sort of questions for the band structure, what you are really asking is if there is any information about the nature of the states embedded in the band structure, which is another way of saying, let's look at topological properties of the bands, because the topological properties are the ones who have this information hidden or yeah. So we said, let's look at Chern numbers. Now, as I mentioned, these bands are degenerate at the K point because the gamma point of the superlattice corresponds to the K and K prime point of graphene. And these are degenerate because the strain does not remove the degeneracy at the K prime points. So in order to calculate the Chern number of isolated bands, we need to open a tiny gap at the gamma points, the K prime points of graphene. And we open that gap adding to the Hamiltonian a term that looks like this, okay? It's an on-site potential with a changing mass sign, that's a sigma z, and we play with different parameters G to open the gap and see how the opening of the gap affects our conclusions. And this is the smallest one, okay, the most accurate one. We play with other values and larger values, and the effect is more pronounced, but we wanted to do it minimal to compare to all the other changes, and we settle on this value, which means we are opening a gap of the order of the micro electron volts at the Dirac point. So this is what these circles represent here, in such a way that we can distinguish a conduction band from a valence band, okay, or a positive energy band from the negative energy band. And we calculate the Chern numbers for the Hamiltonian in the K point and the Hamiltonian in the K prime point. And for 15 degrees separation, we obtain a Chern number that is close to 0, you would say, opposite sign in the K prime point, which is telling us it's okay because graphene is not topological, the total Chern number should be 0, so they cancel, and anyways, it's 0 for the conduction band. For the valence band, however, it's not 0, it's -1, it's close to -1. They cancel overall, which tells graphene is not topological, and you are not going to see these effects unless you break valley degeneracy. So you make the physics of this valley more relevant than the one for this valley. But if you don't have valley symmetry breaking, the total Chern number will be 0, and effectively it cancels. What happens at 45 degrees, which is the other place where we have flat bands? The Chern numbers reverse. Is now the conduction band the one that has a Chern number that is not trivial, and the valence band that the one that acquires a trivial Chern number. So this information is telling us that the states that populate these bands are topological, while the states that populate these bands are trivial. Okay? Now, how come, or where this comes from? Let's make a summary of what we learned until now when we put graphene on a periodic substrate that induces a periodic strain profile. We know that we can open gaps in the band structure. We know that the local density of states separates into two different spatial structures that pretty much mimic the profile of the pseudomagnetic field, or the strain, if you want. We know that for certain orientations, the bands acquire non-trivial Chern numbers. The obvious question is why? Where are these non-trivial Chern numbers coming from? This is the part of the problem that took us much longer and confused us for a long time, until we realized that one way to look at the question is to analyze what happens with the wave function that exists at the K and K prime points of graphene, which is the gamma in the superlattice. Okay? This wave function sits at 0 energy. And if you remember, I mentioned that the 0 energy Landau level was very peculiar to graphene. So let's see what happens to this wave function as we move the orientation from 0 to 15 degrees. If we look at the amplitude square of the wave function at K, and K prime is the same, for the conduction band, so we open a gap, so we have we need to break this degeneracy that exists at the K point, and we break using the same mechanism, adding a term in the Hamiltonian, so we have a wave function with an energy slightly positive and an energy slightly negative. If we look at the modulus square of the wave function that has slightly positive energy, as we change the orientation, you see that the wave function has support, has amplitude in sides A and sides B, so equal quantity in both. And as we start rotating, the amplitudes in side A start to acquire a circular, quasi-circular shape, while the amplitude that was distributed in sides B, it's getting of this shape. Now, I want to call attention to something. Look at the scale of the numbers, okay? The scales here go 3, a little bit lower than 3, a little bit lower, much lower than 3. Here, when we got to this regime, we get to 10 to the minus 26. I don't know if it's visible. But the amplitude of the wave function in this side, it's tiny compared to the amplitude of the wave function in these sides. So, in other words, the wave function at the K prime point in graphene, when I slightly open a gap there, for energy positive, it has maximum amplitude in this lattice structure and minimum here. Let's look at it with a little bit more detail. So we are with an orientation of 15 degrees. We open a gap, now a little bit larger gap, so we can look at the things with more detail. And I look at the amplitude of the wave functions in sublattice A, and I obtain this different set of parameters. And for sublattice B, for the positive energy, as I said, here the 10 to the minus 26, I hope is more visible. It's tiny. I have amplitude here, but it's tiny coming from this wave function. When I look at the valence band, at the solution that has negative energy, the amplitude in sides A are the ones that are 10 to the minus 26, are tiny. Okay, so in the the whole wave function, if you want, doesn't have practically any amplitude here. All the amplitude is concentrated in this region. This is the region that gives me Chern number different from 0. This is the region that gives me Chern number equal to 0. Okay? So that this already is telling me that the Chern number must have to do with these extended wave functions coming from the K point. I look at 45 degrees, and what I see is that the solution for the wave function that has positive energy has negligibly amplitude for the conduction band, here in the minus 26, while most of the amplitude resides on sublattice B in this connected Kagome-like structure. I remember you that the conduction band for this orientation has a Chern number -1. Again, the connection of the Chern number with this structure. The valence band, the whole band, is mostly populated here in these disconnected triangular sides, while the contribution from the 0 mode to these sides is 10 to the -26, it's tiny. The Chern number for the band, for this band in this orientation, is 0. Okay? So clearly, the fact that the Chern number is 0 has to do with the wave function at the gamma point, or the K point of graphene, being localized here, and the Chern number different from 0 has to do with the 0 mode wave function being local extended along these regions. How can I understand that? So the way to understand the intuitive way to understand this is to correlate these charge distributions with the profile of the pseudomagnetic field. Here I am plotting the profile of the pseudomagnetic field for 15 degrees. Here is the scale between maxima and minima. Here is the amplitude of the wave function at the 0 energy for sublattice A and for sublattice B. And here is the total density of state that I obtain at this orientation. If you look at the total density of state for sublattice A, you see that the total density of state follows pretty much what happens with the amplitude, with the square wave function at the gamma point, at the K point of graphene. Okay? So whatever happens to the 0 mode is what happens at the end with the total local density of state, both for sublattice A and for sublattice B. When I look at the profile of the pseudomagnetic field, what I see is that the regions where the magnetic field is negative and small, if you want, the smallness, the dip in the magnetic field is much more shallower than the barriers, which tells me that this state that has 0 energy, okay, the 0 energy state is surrounded by huge barriers, 700 Tesla barriers, and it becomes a particle in a box. I am confining the 0 Landau level here, the 0 pseudo Landau level. And I am confining it in a geometry that is disconnected. So I am literally confining, I'm making particle in a box type of states here, and I am not allowing them to connect. So this is a trivial insulator. And I have a Chern number associated with each that is 0. Okay? When I go to 45, and I am analyzing the energy, the conduction band, just to make things clear, we can repeat the argument for the valence band. But for the conduction band, when I go to 45 degrees, that's when the conduction band acquires a Chern number equal to 1. When I look at the magnetic field profile, I see that the minima of the magnetic field, which is quite deep, is connected. And now the wave function at the 0 mode can have amplitude all over the place following this connectivity. Notice that the total density of state, the total local density of state, follows pretty much the pattern of the 0 mode. This 0 mode that can develop all along these regions, in a region where there is a net pseudomagnetic field, this is a Landau level 0 mode. And it's percolating through the Kagome lattice. This is an extended Landau level, and this is the origin of the non-zero Chern number for the corresponding conduction band in this orientation. will I see any difference if I do an STM experiment between these two orientations? Will I see any signature of these effects? And the sad answer is no, you are not. Why you are not? Because if you have this orientation, this is the density of state per sublattice, this is the total density of state. This is the band structure associated with this density of state. These are the bands. I am only plotting here the conduction band, okay, for an orientation of 15 degrees. I put an STM tip here, and I can put an STM tip here. This is the places where I am going to get a signature, a signal there. As I said, in the 15 degrees here, I will have a 0 Landau level, which will be part of a particle in a box spectrum. But a particle in a box in a very deep box, in a very deep potential well. So I will pick up the signature with my yellow tip of a Landau level there, and the next level, well, will be way above this 160 millielectron volts, because it will be separated by particle in a box type of physics, okay? These guys will not have much contribution of the 0 mode, okay? But it will have contribution of all the other states that are above the 0 node, that have a slightly energy, all these states that disperse and this part here, okay? And they will contribute there. But then, since these states belong to the linear part of the Dirac spectrum, that when I apply the superlattice gets folded, okay? What I am seeing really is that these bands that are folded, and the folding of the bands imposes, the folding appears with a scaling that depends on the superlattice period. So the separation between these bands will depend on the superlattice period, okay? And they will give me peaks in the STM signature, but they will not be Landau level scaling because they are not coming from Landau levels. They are coming, if you want, from the 0 Landau level that is folded. They are not different Landau levels per se, okay? It's like the 0 Landau level that is made up with states beyond the gamma point. So I will not see Landau level scaling in any of the two unless I go to very, very high energies, where I can see the next Landau level that has been trapped by this potential well. If I am at 45 degrees and I will put my tips in equivalent positions, and again notice that the yellow tip is in the circular region, the triangular circle, and the pink tip is in the hexagon, in the kagome, I will have exactly the same situation, with the difference that this tip here will be catching up really the Landau level, okay? And in this region, I could, in principle, capture other Landau levels, and I could see Landau level scaling. But this Landau level will be truly folded, again, because of the superlattice structure. So I will see a peak separation that will have to do with the folding. I will have only one chiral state if I cut my sample here, because I will have a truly developed 0 Landau level, no more than one. And this 0 Landau level will have its corresponding chiral edge states, but there will be only one chiral edge. I will not have many. And this one will capture the states that have been captured by a particle in a box type of physics here. And again, since the particle in a box has a large spectrum separation because the box is deep, I will only see one of those. The difference in STM signatures will be irrelevant. You will not be able to distinguish the topological regime or the not topological regime. In order to see this, you first need to break valley degeneracy and then make your sample finite. So either you can image with STM the existence of the edge state at the edge, or in these particular regions, or do transport experiments and verify the existence of a chiral edge that crosses these bands. But otherwise, this is nice features of a topological transition or a phase transition between different topological phases, but it will be hard to measure. The final thing that I want to comment on is that you can say, well, okay, if I want to open the maximum gap and if I want to have what will be the parameters, so we play with different parameters And the maximum gap for this particular superlattice opens at 15 degrees and 45. So this is a periodic structure with a period of 30. So it repeats 45, you have a maximal gap. And the maximal gap condition also is coincident with the distance, the largest distance between the equipotentials, is the magnetic field. That's another thing that can be evaluated to decide when you will have flat bands with maximum gap. And it also coincides with the maximum contrast between the two occupation of the sublattices. So the obvious question is, this is an effect difficult to see. Experimentally, you have to do a transport to identify these phases. How robust is it? Well, we chose different strain profiles. We chose superlattice anisotropies. We made the superlattice anisotropic by changing this alpha parameter that I mentioned at the beginning. We look at different lattice geometries, square lattice, rectangular lattice, and all these effects can be seen in all these cases, of course, within certain limits. So, the conclusions. We can use periodic deformations to engineer band structures, and you can imagine that this engineering comes only from the mechanical deformation. You can start thinking, oh, what if my substrate has regions with spin orbit and regions without spin orbit? Or is my substrate has regions with, I don't know, superconductivity and not superconductivity? And no, you can start thinking about more sophisticated problems, and I think that this is a good recipe on how to deal with these questions, how to try to find answers. For specific, the orientation of the substrate is very relevant to the physics that it's been observed. This is exactly what happens in twisted bilayer graphene, and it's very tempting to think that in these systems we could also find superconductivity, Mott-insulating phases, and all the zoo that you are observed there. The charge distribution for moiré patterns, in this case, for this particular lattice, they are separated into triangular and Kagome. And by changing orientations, you can produce phase transitions between trivial and topological phases for one valley, okay? So if you want to see this phase transition, you need to break valley symmetry breaking to see the effect of the topology. This work was done in collaboration with two of my ex-students now, Tarek, who recently graduated this past August, and now is an assistant professor back home in Bangladesh, in the University of Dhaka, and Dawei, who graduated a couple of years ago, and he's a postdoc in Hong Kong. And the support was provided by NSF and NQPI here, and this was partially done when I was on sabbatical in Denmark, and I received funding from the Nordea Foundation and this Otto Monster Fund. And that's it. Done.
Thank you very much, Nancy. Very nice talk. So this talk is open to Rafael Costa. He was very quick raising his hand before Edson. So Rafael, please ask your question.
Yeah, thank you, Professor Sandler, for the very nice presentation. I have many questions. I'll try to stick just to the most fundamental ones. Yeah, can you please go back at the Dirac Hamiltonian when you first write it down? It's at the very beginning. Yeah.
I am choosing.
Yeah, when you talk about right there. So for the K and K prime points, the difference is basically the charge, right? That's basically particle-hole exchange, right?
Well, the look that the Hamiltonian has depends on how you write your basis in the AB lattice. So the way that we write it is in a basis that is called the Valley symmetric basis. And I don't know if that I am answering your question. We chose that basis because in this basis, the kinetic energy is the same for both valleys. You see that here I am not using sigma star, which is usually the notation, or minus sigma daga, which happens when you order the basis A, K, B, K, A, K prime, B, K prime. So if you change your basis, you can reorder this basis in AK, BK, minus BK prime, AK prime. When you write your basis in this way, the Hamiltonian, the 4 by 4 Hamiltonian gets split into 2 by 2. Sorry, the 2 by 2 have exactly the same form in terms of the sigma Pauli matrices. So that's why we choose particular basis. Now, when you reorder your basis and you want to calculate physical quantities, you need to remember that when you are looking at the K prime point, the first component of your spinor is not sublattice A, it's sublattice B.
Okay.
You need to keep track. That's the price you pay. But that's why these Hamiltonians take that simple form where the change in sign, it's only the thing that reveals that you can break any of the symmetries of the system.
Okay, thanks. And still here in that slide, you gave a very nice physical interpretation for the scalar potential. I don't know if I missed, but is there something like that for the vector? I mean, it's really remarkable that when you strain, you have something like a magnetic field effect. And I was wondering if there's any interpretation.
I completely agree with you. It's at some level it's still magical, the fact that the picture in terms of a magnetic field works so well. If you look at the strain tensor, this combination, so especially this one, the strain tensor is how the displacement occurs when you apply a force. Both the displacement and the force are vectors. So you can think that you are applying a force in the x direction and the things display in the y direction. So these are called, what's the word in English? Like when you are shearing, I don't know if you see my hands, I am. So when you do shear, for instance, and you create imagine creating kind of vortices that to create a vortex, you have to apply kind of a torque, right?
Okay.
To create circulation. Well, the epsilon xy, for instance, is the strain component that has to do with shear. And so moving in a direction perpendicular to the application of the force, which, if you think about it, is what's exactly what the Lorentz force does. Right?
Okay.
So the components of the strain that induce shear and that you move these things, you push things in one direction, but the atoms is placed in a different one. It's reasonable to think that they are mimicking the effect of a magnetic field, because that's what the magnetic field has, an orbital motion.
Right. Nice. Now, well, if I may proceed with with the inquisitions.
How many do you have?
I just more 3. I think that's, they're quick. I don't know.
Okay.
Yeah. When you first show the flower patterns that you've dubbed flower pattern, right? Yeah, there. I was wondering, just a disclaimer, I'm not familiar with the area, not so much, okay? So don't laugh at me for my dumb questions. Probably I'll make very much of them. So I was wondering, why are the yellowish, whitish spots, they are much brighter and bigger than the blue, where the blue ones are blue. Why is that?
It's an optical illusion. I know what you're talking about. You have no idea how many times I ask my student to redo the picture because I have the impression that the whitish was brighter than the blue. Yeah. However, typically they have the same magnitude. So we weren't good enough with graphics, I would say, to choose a color palette that that numerically they have exactly the same value. Yeah, I check. I work with numerical data many times, but it's an optical illusion. It's interesting how because you think you are seeing things when in reality there is nothing there.
Yeah. And now, what about? I was wondering also when you do the strings, you do these smooth deformations somehow in comparison to the lattice, the lattice parameter, right? I was wondering, did you play with the size, or the size of your Gaussian over there, and what happens when you approach something like quote unquote discrete strains, or I don't know, does that just simple defect physics, or you see something in the transition from there that's interesting?
Okay, so this picture, this description of graphene in terms of this Hamiltonian automatically implies that you are not seeing each atom individually.
Okay.
The atoms collapse in one point, and that point is a point in space. Okay. And that's why each point is described as if it were a spinor.
Okay.
The picture that we have of an electron carrying an internal degree of freedom that is a spin, well, when you use this Hamiltonian, what you are doing effectively is to reduce the unit cell to a point. And in that point, you draw an arrow. And that arrow represents if it's up, side A, and if it's down, side B of the two-atom unit cell. Now, this is clearly an approximation. And it's an approximation that is valid as long as you are close to the part of the spectrum where you see the linearity. Okay. Now, you can ask, how close is that? Well, I was in a conference not long ago where people reported that when they expected to see the Dirac point, they see a tiny gap of the order of the microvolt. And that tiny gap of the order of the microvolt is expected to come from spin orbit effects, which in graphene are supposed not to exist. So it's a question of resolution eventually. So at some point, this is not valid anymore. So from the point of view of the mathematics, I would say that if the lattice, let's say in the Gaussian that we use, if the width of the Gaussian is of the order of 10 lattice constants, then I wouldn't trust the model.
Okay.
Because there are few atoms there, and I am assuming I have something that is truly discrete, and I am describing it as a continuum. And
so that then Dirac equation won't any longer describe the effective physics. Okay. Yeah, and final one, I promise, is when you calculate the Chern number for the conduction and valence bands, you see something like minus 0.03 and the other one 0.97. I was wondering, is there anything special to the fact that the modulus of their difference is precisely 1? Because it's almost as if you calculate the winding number clockwise and then counterclockwise in a closed trajectory, and then it's 1.
The fact that it's 1 is telling us that there is only one chiral X state coming from one Landau level. That's why we know that the other peaks that you could see in an STM signature, as I was claiming here, these other peaks will never show Landau level scaling because there is only one Landau level in this system. That comes from 0 Landau level. It's a 0 mode that gets folded because of the superlattice. Now, it gets folded, and if it's trapped in the circular region, it's trapped in particle in a box. And on top of this folding, you will have the particle in a box levels. And that's the scaling that you are going to see. But if it's folded, and when it is folded, lies on these Kagome-like structures, there is one Landau level that is folded, and there is only one edge state associated with that Landau level. And that's why the Chern number is 1.
Okay.
That's our current understanding, at least. When we send the paper to publish. We'll get the reviewers, and we'll probably learn. We'll have more feedback about it. But yes.
Yeah. Thank you very much once again for the very clear presentation as well.
Edson, so it's your turn.
Okay, I have just 15 questions, Nancy. Sorry. Thank you very much for your nice presentation. It's always nice to see your presentation. They are very pedagogical. I have a comment on Rafael's question, and he mentioned that the charge is different K points. In fact, apparently, the interpretation is the magnetic field the opposite, different K points. Right, K prime. Yeah, I think that's my point. That is so. I have two questions now, and they are connected to each other. First, when you calculate your Chern number, you are calculating actually your charge distribution.
I compare both. Well, to be honest, to truth, I didn't calculate any of them. They still does it, but yes, we calculate.
Okay. Right. Yeah. When I say you, and including everybody.
Exactly. Yeah. Thank you, Edson. Yes, that's a fair statement. Yeah, we try to correlate the charge distribution with the Chern number to find if there was some type of connection between them. The reason was because we were hoping to see Landau level scaling between these bands, and we didn't find Landau level scaling because we were biased with this picture that when you have a strain, you have Landau levels, and that picture is wrong. When your strain is inhomogeneous, what you have is magnetic barriers, magnetic field dependent on the position, and that will not give you Landau levels. So I go with your question. Sorry for.
Okay, don't worry. But in this, since you are in this slide, let me. If you increase the G, the 0.07 will not decrease.
No.
Okay. Okay. No. That's what
with values of G from 0.1 to I think one order of magnitude smaller than the one that I am showing. Because we wanted to show that what happens for the pristine graphene, and these numbers were robust. So in the beginning we got, I don't know, if you increase G, we get 0.09, let's say, or we even go to 0.1, no? But we never, no.
My last question. So if you were looking at the weight of a spectral function of the wave function, and the modulus square, right? So and they are opposite. If you look at the conduction or valence band.
Yes.
And so in connection to that, if you want to calculate transport, like you said in your conclusion, so it means that if you change the chemical potential, put up there or down, so you have the same how to say signature, right? One for whole and for
assume. So here, for instance, is one for this orientation, the conduction band and the valence band. And the valence band, I don't know if you can see it. Let me put it bigger. But the contribution. So I think of this as bound states, as trivial bound state. It's a zero mode, okay? It's not any bound state. It's a zero mode, but it's a trivial bound state. And here, the contribution of this bound state is negligible. So I am not going to see this. Oh, sorry. The contribution here is large for 15 degrees. Okay. Now, if I change the chemical potential, oh gosh. If I change the chemical potential and I go to the valence band, this state has negligible contribution. So in the valence band, I will see these guys. So these will be the holes. And the holes will have Chern number -1. So if I change the chemical potential, I will go from a trivial insulator to a topological insulator.
Ah, okay.
That's what basically for this orientation. If I go to the 45 orientation, I go from in the conduction band here, I have my Landau level, let's say. I have the Chern number equals to -1. So I go from the topological phase, I change the chemical potential, I go to the holes, which is here, and this the trivial insulator. So that's the idea. Yeah.
Mm-hmm. Thank you, Nance, for answering my question.
You're welcome.
Nancy, I know that you are tired. It's almost 2 hours that we are talking, but I have two quick questions.
Talking at other moments too. If you have, seriously, for me, this is the first time that I tell the story, and I'm trying to find a way to tell it that is, simpler and yeah.
Okay, yeah, it's I understand that. I am trying to gauge how similar is the physics that you are seeing to the very narrow physics that I learned about the twisted bilayer graphene. I am having a collaboration with Luis Diaz and one of his students on TBG. And I understand that in the TBG, when you are describing you are changing the chemical potential and you are filling up the flat bands, you are putting electrons only in the moiré lattice, only in the sides of the moiré lattice. Is that true here also?
Well, I think okay. Let me preface my answer. The answer is it's true in this orientation. Where I put the electrons, I will be putting them in the conduction band, and this conduction band corresponds to the moiré lattice sides of the triangular lattice.
Okay, and there is a large distance in atomic spacing between these places, right? It's like nanometers.
Exactly, nanometers.
Between these sites, okay.
Measuring units of the superlattice period,
okay.
And the superlattice period is 14 nanometers for this calculation. Okay. So it's of the order of 30 nanometers here.
Okay.
2.5, 3. Okay.
Okay.
So that's why. Now, if I am at this orientation, you're kidding me. Very sensitive. So if I am at this orientation and I start putting electrons in the conduction band, you're kidding me. The electrons will go in this kagome.
Okay, but you see that too in the TBG, because they are interferences. There are interferences that are constructive and that are not in the sites of the moiré. So it's very, very similar in reality.
Okay, so having said that, I never work on the TBG, but when I saw the moiré patterns in the TBG, and I look at the models that people use, the continuum models that people use to represent, to describe, especially there is this model by Vishwanath et al., Ashwin and company. The Hamiltonian that they work out, it's pretty damn similar to the one that we are working on.
Okay, it's very similar.
Very similar. In fact, one of the proposals that we are writing, the thing that I am proposing is to precisely study what's the difference between the two. Because you have more symmetries coming from the fact that you have two layers, but you project the electrons only to end up with a 2x2 Hamiltonian. So instead of working here, you end up where if you work in one valley, you also work with a 2x2 Hamiltonian. And the symmetries, the spatial symmetries and the time reversal and inversion and all that, that's what I wanted to look in more detail, because my suspicion is that it's the same physics.
Okay.
I think that we could get superconductivity here too if we add photon.
Yeah. Okay.
has this phonon mode that it's very, very soft, the flexural mode, that it's out of plane. That's why it's
well, maybe you get superconductivity if you add interactions too.
Yeah, that's the other thing. That's something that Tarek was interested in learning, how to calculate with interactions. And yeah, now that he's back home and he needs to start teaching, it will take a time to put some.
Okay. But we are using RPA to look for superconductivity. Because sorry?
I think this is important, especially in the flat band region, right?
Yeah.
Flat band. Yeah. You are thinking about the flat band geometry.
Yeah. Because I used RPA for the nuclides, and it can be, well, it's a mean field approximation, so when it's a low-hanging fruit, let's say, because it can be applied there. The other question I was going to ask is, you kind of answered it because you already mentioned that you would be looking for one edge state only, but I assume that you didn't do any calculations for nanoribbons, because you can make a nanoribbon out of that and then do the...
I don't have, well, that was my question. Do you have students who are willing to do this? Because my current problem is that I have one student that is working, just started this summer, and working on quantum in qubits in optical cavities. So I am learning like crazy optics, basically.
Okay.
But I don't have another student, and I don't want to take a student. I am teaching the first year students, and I don't want to take anyone until they finish the first year.
Okay.
Know how they are doing. So I am lacking slaves.
Slaves. We have some slaves here.
So if you have a student who, we can start thinking about these problems, because I think there are lots of things that the model is relatively simple. We understand it quite well. And we can start thinking about implementing something together and having each other in person.
Rafael is probably will make a comment about the slaves joke.
Rafael, go ahead. For those who are offended, just trade slave by auxiliary, and that's fine.
But we don't sell them. We don't negotiate.
It's sad, but with this issue of the figures, I notice how much dependent I am with students who are skillful to do these things, because Tarek is very good in analytics and analyzing, but not so much with making plots, and it was really a learning curve for both of us, how to work with these things. So, yeah.
Well, the plots look, compared to mine, the plots look very nice.
Yeah. I'll tell him, he will be very happy, I'll tell him.
Well, let's see if there are any other questions. Anyone? We still have...
I saw your comment in the other, Gina Tom wrote, hi.
Yeah.
Knowledge, yes.
And Rafael wrote an interesting one here about the Hofstadter's law.
Yes.
Always takes longer than you expect, even when you take into account Hofstadter's law.
Yeah.
When you mention about how long it may take when your advisor says that, this is easy, you can do it in a week. It may take months.
Yes, exactly. Well, that's exactly what happened. When we say it's periodic, we can use Bloch, we can diagonalize the Hamiltonian, and yeah, that part was relatively straightforward. But when we started looking what happens with the wave functions, we were completely lost, literally lost. Especially because I have to say I was very biased with this Landau level scaling. I was sure we should find the Landau level scaling, and there was no way. And no way. I understand why now.
Okay.
Okay. Well,
so if we don't have any more questions, we should thank the speaker again. Thank you very much for this very nice talk. I'm gonna be writing you an email to ask for the slides, if you please.
yes, definitely.
We will post them with the video of the talk in our